office hours change tomorrow, right? Okay. Well, there are some new people in this class, not in that class, so let me say that again. Tomorrow my office hours are changed, or at least I think they will be changed just slightly. I had a doctor's appointment yesterday, so I had to miss my trig class. And tomorrow, normally I have office hours from trig classes over at 10:45 until 12:30 when my physical science begins. But because I missed yesterday's trig class, we're planning right now to double up and do 2 classes tomorrow. So it'll be 9:30 to 10:45 and then 10:45 to 12. So my office hours are shortened only to 12 to 12:30 tomorrow, if they go along with that. We talked about it last time, and that's when they thought they would do it. But if no one can come, but they can come Tuesday, then I'll wait and do it Tuesday. So anyway, just wanted to get that one in there too. All right. Now, Section 10.1, we finished that, right? Everything? Okay. 10.1, let's talk about sequences. And if you think, what is a sequence? It's a set of numbers, okay? Generally, you expect them to have some pattern. And I guess always they have some pattern, but some patterns are really hard to see what the pattern is. But usually there is some connection between those and there's something. Now, how does a sequence differ from a series? A series is a sum of the elements of a sequence. But it's not just there, okay? That sum, because it's an infinite sequence, that sum is an infinite sum. And of course, none of us can sum infinitely, okay? We can sum, but we have to terminate somewhere, but never mind. If, however, if you think about it, if you're just summing partially, and here is, believe it or not, a sequence, a series, an infinite series, and it is indeed a value. This is, and by the way, this is what your calculator does when you tell it to calculate a sign. Okay, just show this here. Okay, we finished 10.1 last time. We're on starting 10.2 today. Okay. And believe it or not, this is what your calculator is doing. It doesn't have stored in its memory somewhere what the sign of 1 is. It's doing an infinite series. It's not doing it infinitely. It's checking at the end of each time to see if the last result is any different from the previous result, basically within some error range that the calculator accepts, like maybe 10 to the minus 14th or something like that. If it's within that, then it stops and says, that's all the digits I can display anyway, so I'll go ahead and stop, okay? So this is really how your calculator, if you were to plug into it in radian mode, sine of 1, starts with the number 1, you know that's not it, subtracts off 1 over 3 factorial, adds 1 over 5 factorial, subtracts 1 over 7 factorial. Believe me, it's not going to be long before you're within 10 to the... In fact, let's do it. If you got your calculator, and you know the factorial key, are you familiar with that? Okay. So let's just try this one. In fact, that's what the rest of this page is doing. Let me see if that's on the slide too. No, it's not. So let me go back. Heighten this again, zoom again. Okay. Okay. Start with the number 1. Can you find that? Okay, good. Okay. Minus 1 over 3 factorial. You have to go to a math key or something like that. Yeah, so it's a bit of punching, but you can get it. Plus 1 over 5 factorial. Oh, what did that give you? 1 over 5. Okay. Let me start writing. I know this one gives you 1. And whoops, I got to get my pen. Oh, I can't write on here, that's right. Okay. Let me get my pen activated. Okay. So that gave you 1, and when you subtract 1 over 3 factorial, what does that give you?
5, 6.
Say again?
5, 6.
5, 6, okay, that's 0.88833333, okay. Add 1 over 5 factorial. Okay, is yours going to stay in fraction mode, or will it at some point go to decimals? It's 10.2 on page, oh yeah, you're in the old book. Somewhere around 523, probably off a little bit there. It's summing an infinite series. Yeah, okay. Second? Okay, well, we'll try it. What did that give you after you added? Over what? 120. Okay. Can you quickly see what that is? I mean, just actually do that division. I can't do it in my head too quickly, so I could do 5, 6. Okay. 4, 1. Okay. Or 842. So you see, this was 8,3. Now we're 8,4. Subtract 1 over 7 factorial. Eight, 4, 1, 4, 6, 8. Okay. Add 1 over 9 factorial. Okay. Look at that. We're good to 4 decimal places and almost the 5th. Subtract 1 over 11 factorial. Stops there?
0, 9, 8.
Okay. Okay, and the last was 7, 1. So we're almost to the limit now. I mean, and that's just a few terms. Of course, your calculator did those calculations a lot faster than you did punching them in, and that's how it came to its answer. Now do sine of 1 and see what you get. Be sure you're in radian mode. 7. We got it. I mean, we're already at there, the same precision you had in yours, right? So that's exactly how it got it, okay? That's an infinite series, okay? Well, it's not an infinite series. We stop somewhere. But if you think about it, sort of seems like we're going in circles. A sequence, this could be a sequence. 1 over 3 factorial, 1 over 5 factorial, 1 over 7 factorial, 1 over that, or put the plus or minuses in there. That's a sequence. But when you put plus or minus signs in between, now you've got a sum, which is a series. But if you think about it, where we had the number 1, then we had this number, then we had that number, then we had this number, then we had that number, then we had this number. That's a sequence again, okay? So basically what you wind up with is a sequence of your partial sums. That's what they call when you just do, you can't do an infinite number of sums. You do a partial sum, and the sequence of your partial sums, if that's converging, then your infinite series is converging. So basically, that's what we've got here. And they actually show this in the text. The S5, that's 1, 2, 3, 4, 5, that's us up through 9, 1 over 9 factorial. That gave you 0.8414709846. 709 846. Probably beyond what your calculator could display. Oh, is that what you had? Okay. And when we did it again, minus the 1 over 11, 0, 9, you probably still had the 8, 4. Was that still a 6? No, when you did the minus, well, what was the sign? What did that come out to?
It was an 8 instead of 6 at the very end.
0, 9, 8, 8? 848. Okay. All right, so you did have one more than they did. So you see, actually we were within 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places after just 5 terms. That's pretty good. That is very good. It's very good. Marcus is here too. Okay. So we're just missing Faith. I hope Faith will get here. I don't know if you know. She added to class later. I don't know if you were here that day. Okay. All right. So basically, this is, you start with a sequence. Then if you decide to add those up, you get what is sequence. But you can't really add an infinite sequence, so you basically terminate somewhere. You have a partial sum, and if you just keep adding more terms, you have different partial sums, which again forms a sequence. Okay, so it's sort of like it's going a ping pong game or something. It says on their calculator, they actually go 0.8414709 848079. The book carries a few more digits, and we were already within, very, very close to that. I would say close enough for government work. Okay, you can get by with that. Most of the time, if you got 3 significant digits, that's about all you can handle. 3 decimal points. That's about it. Okay. It says we can see the S5, which is the partial sum after 5 terms, differs from sign 1 by less than 10 to the minus 9th, which means that is a very close approximation. This suggests that partial sums converge to sign 1, and in fact we'll prove that. And here's what it's actually saying, that the sine of 1 is equal to the limit of, as n goes to infinity, of your s sub n, which that was the nth partial sum. As you get n get larger and larger, your partial sums, you're adding more and more terms to it. Shoot, you can't get any more precise than the calculator. After we did just 5 terms and got awfully close, 10 to the minus 9, probably in another term or two, you're going to be beyond what the precision of your calculator is. So yeah, you're there. But technically, you're not really there until you go to infinity. But you don't have to go that far, because we don't have calculators that'll go that far anyway. Okay. In general, an infinite series then is an expression of the form, the summation, just like you see here, of n equal 1, or some value, sometimes it's not 1, to infinity of a sub n. Okay, where a sub n is a sequence. Okay, so that would be a sub 1 plus a sub 2 plus a sub 3 plus ... all the way up to a sub, well, you're just going a sub n, and you just keep on trucking. Okay, it just goes on forever. Okay, because you're letting n go to infinity. So I really shouldn't have stopped there. It just keeps on ... dotting. Okay. Now, where a sub n is any sequence whatsoever. Okay. Now, of course, some of the weird, odd sequences that we fiddled with, like the digits from the square root of 2 or something like that, No, when you sum those up, you don't do it unless you put enough zeros in front of it, so there are some that, wouldn't make really good, reasonable series, but so let's look at then how we express some of these things. I think, okay, this is the slide. I was going to write, but it's here, so I won't write it. I'll just zoom in on it. Okay, here's a sequence of numbers. 1/3, 1/9, 1/27. Okay, what seems to be the general term here? 1/3 to the n, exactly. You could also say that's 1/3 to the n. That would be 2, but 1/3 to the n. So the a sub n would be 1/3 to the n. Now, that's the general term of that. If you were going to do the infinite series from that sequence, and let's just put all pluses in between, how do you do it make them alternating signs? You use a -1 to the nth power, or n plus 1 power, whatever it requires to have that in front of it. Because these are always sums, usually not differences, but if you put a -1 to the n, then every other one's going to be a negative and every other one's a positive. Okay, so if you were to add those together, it would be 1/3 plus 1/9 plus 1/27 plus 1/81. Now, I want to point a couple things out to you. It's really obvious to me that sequence is convergent, right? What's it going to? 0, of course. These are getting smaller, 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 really pretty rapidly. But with a series, you're adding things to it. And this is always an addition, so if you keep adding to something, will you converge there? Sometimes yes, and sometimes no, unfortunately. This one I'm pretty sure does, and we'll get to that later. Okay? Here's another one. 1/1, 1/4, 1/9, 1/16. What do you reckon that sequence is? One over n squared, exactly. 1/n squared, okay? Or 1/2, well, no, 1/n squared, that's it. 1/n squared. Now you start adding those together, be 1/1 plus 1/4 plus 1/9 plus 1. Okay. Now, just looking at these two, these numbers are getting small faster than, these are getting small faster than those, okay? And I think you realize that this is a power, this is an exponential series, sequence, and this is a power, okay, with the same power. This wins. That gets small, fat. I mean, the 3 to the n gets much bigger than n squared, okay, much more quickly. So in the denominator, it gets smaller and smaller numbers. So I could be convinced this one could converge, and this one may not. Now they both may, or they both may not, but this one certainly, the numbers are, each subsequent term is much smaller than the previous one by a lot. These are smaller, but not by as much. So can't say for sure if either of these converges, but if one did, if only one did, I'd know it would be that. It could be neither do or both do. Okay? So, now we're going to talk about convergence. Okay. Now remember, you start with a sequence, start adding those entries from the sequence. That gives you a series, but then you just take so many terms of the series, and that gives you another sequence. S of n, if n is 1, that would be just the first term. S of 2, capital S of 2, would be the second partial sum. 1 over the first term plus the second term. S of n would be the third partial sum, the first plus the second plus the third. Okay. So in infinite series, the summation from n equal k to infinity And like I said before, you don't have to start at 1 or 0. It could be any number there. Usually the k's are positive, okay? I can't think of many times we would start with a negative k, but they need to be integers for any sense. So it just looks strange to do it. So usually they're always integers, usually positive integers, and when you're summing, k's going up by 1 each time. Okay? So this is a sub n, where n is your subscript here, which means the nth term of that sequence, but you're summing those up together. That converges to the sum s if the partial sums, which now forms a sequence, remember, the limit as n goes to infinity of s of 1, s of 2, s of 3, s of 4, which are the partial sums from a sub k plus a sub k plus 1 plus a sub k plus 2 plus a, yeah. So you have partial sums in a series, and that forms a sequence. If that sequence converges to some number, s, then we say the infinite series converges. In this case, we write s is equal to, if it does converge, the summation of the sequence. Okay? Now, if the limit does not exist, we say that the infinite series diverges. If the series limit is infinite, we say the infinite series diverges to infinity. Okay? Now, we showed examples of diverging sequence that didn't necessarily go to infinity. Plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 never converges or diverges, but it doesn't go to infinity. Can a series do that well? Yeah, as well. Yeah, it probably can. Okay? In fact, you could come up with one pretty easily to do that, and it would could diverge, but not diverge to infinity. But if it does get infinitely large, then it diverges to infinity. Okay. I think this is example 1. I'm going to zoom in on it. Well, no, I don't even want to zoom on it. I think we need to write on it. Investigate this one. S, that stands for series. S is the summation. You could think of it as a sum too. Okay? N equal 1 to infinity of 1 over n times n plus 1. Okay. Now, you write down for me, or tell me what to write down for the first several terms of that. What would be the first term when n is equal to 1? One over 2 plus 6 plus 1 over 12. Yep. Plus 20. Okay. And we'll just let the rest go. Now, looking at them that way, that's going to be hard to add. I mean, you could add them. I mean, you got calculators, you could do it. You could just keep on trucking, see if they do. There's actually an easier way, though. Okay? And they've done that, except they jumped right on up there to n equal 10 and 50 and 100, 200, 300. What does it looks like it might be doing? Going to, just from this chart here, looks like it's going to 1. But it's going there awfully slowly. I don't want to have to write out the first 300 of those terms, and add them together. My fingers would get tired. My head would get even tired, but yeah, not too good. Is there an easier way to do this? Okay, these are the partial sums. Well, let's write that slightly different way. 1 over 2 plus 1 over 2 times 1 over 3, right? Plus 1 over 2 times let's see. Two squared times 3 plus 1 over. Nah, that isn't it either. I thought I was seeing a pattern there, but I'm not. Here's the trick. Remember back in Cal 2 when we had a integral that was looking like that? What did we do to it? What's the technique? Okay. See if this rings a bell. 1 over n times n plus 1 is the same as a over n plus b over n plus 1. What do we call that technique? These are fractions, partial fractions. Okay, it's the technique of partial fractions. So let's see what we've got here. This would be, let's see if we can do this quickly. This would be 1 is equal to, let's see, I think what we did there was multiply both sides by n times n minus 1, right? It would be 1 times a times n minus 1, n plus 1 plus b times n, right? Multiply both sides by the denominator, n times n plus 1. You see how that would work? Would it help to put another step in there, or you see it? Okay. Multiply both sides of this by n times n plus 1. Multiply this by n times n plus 1. Multiply this by n times n plus 1. Right? Here, everything goes out, leaving you 1. Here, the n's go out, that gives you that. Here, the n plus 1 go out, that gives you that. Right? Now, the next step, to me, always seems fishy. Why would you do such a thing? Well, here's what they do. They say, well, let's let n equal 0. Well, wait a minute. N can't be 0 up here. Why would you set it to be 0 here? But let's see what you get. Let's see what you get if you let n be 0. So let's plug in n equals 0. Doesn't seem fair to do, but you can do it. And here you would have 1, because there's no n there, is equal to a plus 0, right? So a is equal to 1, right? Now, since that works so well, let's let n equal, or n plus 1 equals 0, okay? Meaning that n is equal to minus 1. Plug that in, you still have a 1, there's no n's over here, and here we have, if n plus 1 is 0, that's 0, and this would be minus b, because n would be minus 1 times b would be minus b. So that means b is equal to minus 1. So now, what that has done for us, 1 over n times n plus 1 is exactly the same as 1 over n minus 1 over n plus 1. Right? Because your n is 1, your a is 1, and your b is minus 1. So that gives you that. Okay? Now, let's do the sum now. The summation, ooh, that's ugly. N equal 1 to infinity of 1 over n times n plus 1 will be the same as the summation of n equal 1 to infinity of 1 over n minus 1 over n plus 1, right? We just shown that, right? So let's do that summation. Okay? Started with 1, what would that be? N equal 1. 1 minus 1 over 2 plus, do the next one, n equal 2. 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5 plus, you get the idea? Okay. Guess what? These two add to 0. Those two add to 0. Those two add to 0. All the rest of them add to 0 until you get up to 1 over some n out here that is huge. And 1 minus that would be 1. So that gets there a lot faster than doing this. Okay? But you just happen to need to notice that you could rewrite that in a different form, which actually to me looks more complicated than this form. And yet that gives you a much quicker view. Okay. Now, this is Cal 3, I realize, but I'm going to give you a quote that my calculus professor when I was in college gave. Back then we were on the quarter system, so we had 5 quarters of calculus plus 1 quarter of differential equations. Well, we finished Cal 5 with about a week or 2 to spare. He said, well, let me get you ready for differential equations because all of us are going to be taking it. And he started showing us some things about it, how it built on calculus and stuff, he said. And really what differential equations is, you try something. He said, you try a trick. And if the trick works a few times, call it a method. Okay? Well, this is what we're going to do. If you have something here that you try and do things, it happened to work if you did partial fractions with it. So if you have a denominator that's a product of things, and you can't see what the easy way to develop what the sequence is going to add to, try doing a trick. Use partial fractions, see if you get a different sequence. It's the same sequence, but just written a different way. Does that help you see the answer better? If it does, it's a method, okay? So try it. So that's one thing you can do. And that's why they call it a telescoping series, okay? Because after that first entry, everything else starts canceling out until you get 1 over such a large number down there. You say, okay, I'm tired. I'll stop here. That's going to be negligible. It's going to be 1. It's going toward 1. Okay. And they basically did the same thing there. So let's look at example 2. I don't think example 2 has a... Oh, this is... Okay, this is doing exactly what we were doing. Kinda. Okay. Maybe a little more elegantly. Your partial sums, the nth partial sum, we didn't do them all, but the nth one was 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 4 plus 1 over n minus 1 over n plus 1. Okay? And you'll notice the minus 1/2 and plus 1/2 adds to 0. Minus 1/3 plus 1/3 adds to 0. All the way up to minus 1 over n plus 1 over n adds to 0. And you're left with that. So you're left with 1 minus 1 over n plus 1. As n is going to infinity, this is going to 0. 1 minus 0 is 1. So that gets there a whole lot faster than 300 partial sums that they showed us before. That I wasn't about to do. Okay. Okay. And notice how slowly that was getting to 1. I mean, it's pretty close to 1, but you couldn't absolutely be sure unless you did it. Okay. Now, before we get to that slide, let's do example 2. Sequences versus series. I've already been telling you so. Discuss the difference between, what does this represent? Second? That's a sequence because it's a set. Those braces mean set. What's in there is a set. A over n is a general term for that set of numbers. So that's a sequence. Okay? Discuss the difference between that and the summation of n equal 1 to infinity of a sub n. Okay? Well, that's taking the elements of your sequence and adding them together. Okay? And that gives you a series. Okay? Now it says discuss the difference between that where a sub n, this looks familiar, doesn't it, is equal to 1 over n times n plus 1. That's the one we were just doing. Okay? Now, if you look at the sequence of those numbers, a sub n, that's what we started with. 1, when n is equal to 1. No, when n is equal to 1, that's 1/2, isn't it? The second one in that sequence would be 1/6, wasn't it? 1/12. Comma. Wait. One times 2, 2 times 3, 3 times 4, 20th, yeah. 1 over 30, right? Yeah. And 6 times 7, 42. That's the sequence, okay? That sum, that's going to be a number, okay? But it's going to just add all these things together. So the sequence, n equal 1 to infinity, is rather than commas here, it's going to be the sum of these things added together. I'm being really lazy here, but that's it. And that would be the partial sum. That one happened to be the 1, 2, 3, 4, 5, 6 partial sum, S sub 6. But we know, looking at it another way, it's going to be this. And that's a lot easier to deal with than that. But that's the difference. It's pretty obvious to me that the sequence, that's going to 0. Okay? The sum, however, looking at that, it did seem like it was going to converge, but it wasn't real clear. After a while, it would be. That's probably converging to 1. But when you do it that way, you see, yeah, it's got to be converging to 1. Okay. So the sequence converges to 0. The sum, in this case, happened to converge to 1. It could be you have a sequence that's converging, that the sum, the series never converges. Or the sequence is converging, well, let me leave it like this. If that sequence isn't converging to 0, there's no chance that the sum is going to converge, period. Because those individual entries have to be getting smaller. If they're even going to 1/3 or 1/10, but you keep adding them, you're never going to get a sum because you're just adding 1/10 plus 1/10 plus 1/10 plus 1/10. That's never going to converge. That's going to get infinitely large after a while. So basically, I'm jumping way ahead here. If your sequence doesn't converge to 0, there's no hope that your series would converge. That doesn't mean that every sequence that converges to 0, the series would converge. Not necessarily. But if it doesn't converge to 0, there's no hope that the series will ever converge. Okay. I'm sorry, I jumped ahead. But let's see what the next theorem says. Okay. Linearity of infinite series. Now, this is a series. The summation of a sub n. Here's another one, the summation of b sub n. Now, they didn't put down what the limits are here. This could be n equal 1 to infinity and b n equal 1 to infinity. Could be n equal 17 to infinity or b, whatever. But whatever they are, let's say both of those converge. Then, this is the theorem, the sum or the difference of those and the scalar multiple of either one of those also converge, for c being any constant. Not an infinite number, a constant. Some constant. Huge constant, still a constant. Okay? And let's get what they are. The summation of the sum of two sequences, summation of the sum of two sequences, the sum of the summation of two sequences is the sum of those two sequences. Okay? The difference of the summation of two sequences is the sum of the difference of those sequences. And the sum of a constant times a sequence that does converge, the summation that does converge, is the constant times the sum of that converging sequence. Okay? So basically, none of you are in linear algebra yet. Oh, yeah, you are. Okay. Oh, yeah, both of you are. Okay. We'll get to something later. This looks just like what and that's why they call it this, the linearity principle of just by anything, matrices or anything else, that if we'll get there. That's why I say, sort of pay attention to this, you'll see it again later. If these two conditions are met, then we have what we call a linear system, okay? And when you do linear programming and all that kind of stuff depends on this property being met. It works for infinite series. It works for lots of things in real life, in the field of mathematics, everywhere. Okay, that's the linearity of infinite series. Okay. Now, they do have a little proof here. And part of that proof, well, it's not really, no, sorry, take that back. After that proof is done, they have a new paragraph starting, but they really don't separate the paragraphs very well. That's why it's sort of messed with my mind a little bit. This proof only goes down to that second blue dot and the line right below that, S of 1 equal 1, blah, blah, blah. Okay? This, by the way, is showing a partial sum. In fact, no, sorry about that. The proof only goes to like 3 lines up there. The next thing is, they're not separating the paragraphs too well. A main goal of this chapter is to develop techniques for determining whether a series converges or diverges. It is easy to give examples of series that diverge. For instance, let me do this first. The series, capital S for series, the sequence starts with S2, but think of that as a sum, series, sum, technically a partial sum, but we'll just go with the sum now. This is equal to the summation from n equal 1 to infinity of some little old number like 1. Okay? Does that series converge or diverge? Certainly the sequence converges to 1. That'd be 1, comma 1, comma 1, comma 1, comma 1, comma 1. Yeah, that's 1 and it's always 1. The sequence is 1. Is the sum is the series converge. If you're letting n go to infinity, that'd be 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Keep growing, growing, and growing. Yes, it diverges. Okay? For sure. Okay? So like I said, it's sort of easy to show examples that diverge. This one might be a little more surprising. Here's another one. The summation from n equal 1 to infinity of negative 1 raised to the n minus 1 power. Give me a few terms of that. When n is equal to 1, what do you have? Second? 1, exactly. Plus, because this is a summation, when n is equal to 2, what do you have? Negative 1, you're absolutely right. So rather than doing a plus, I'm just going to make that a minus 1. Okay? Plus, when n is equal to 3, it's 1 again. Next one. Minus 1 plus 1 minus 1 plus 1. Now, certainly, that sequence, 1 minus 1, 1 minus 1, 1 minus 1, that is a sequence that doesn't converge. It doesn't diverge to infinity, but it doesn't converge. How about the sum? What does that do? The first partial sum is 1. Second partial sum is 0. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. It doesn't diverge to infinity. It doesn't get infinitely large, but it never converges. It's a new sequence that doesn't converge. Okay? So, as I said, it's sort of easy to give examples of series that diverge, that do not converge. Here is a series made up of a sequence, and it's called the geometric series. So I'm going to erase the stuff that's here. Okay? A geometric series, and we use that same term, didn't we, for a sequence? Has nothing to do with geometry necessarily, it's just a geometric series. Okay? With common units r not equal to 0, and I'm pretty sure we usually let common ratio r, then the series is defined by a geometric sequence. Geometric sequence is c r to the n, if you remember that, as long as c is not equal to 0. Okay? I do think they allow c to be positive or negative if you need them to. If you begin the series at n equals 0, then here is your sum. Okay? The series would be the summation of n equals 0 to infinity. That is your common term that was in your sequence, c r to the n. Okay. Now, give me the first term in that sequence, in that series, sorry. C, is that what you said? Yes, that means yes in Spanish. No, right, okay. Plus, and what's the second one? Okay. CR plus CR squared plus CR cubed plus CR to the fourth plus dot, dot, dot. Okay? Now, one thing you could do with this is factor out a C. And what you're left with there is 1 plus r squared plus r cubed plus r to the 4th plus dot, dot, dot. Okay. Now, let's just think for a moment. Okay? Maybe a little longer. Certainly if that r were 1 or greater, blowing up, right? No way that would work. Okay? Now, are we guaranteed, though, if that r is less than 1, will that work? I don't know. Let's see. Okay? I was thinking this is going to tie with this, but it really doesn't. I don't think. Yeah, it might. Yeah. All right. Here, I think what they've done is taken C to be 1/2. All right. Let's not worry about that yet. We'll get to that in just a second. Okay. Now, yeah, that is what they're doing. No, they let C equal 1 and R be 1/2. That's what I was thinking it was. So for right now, let C equal 1. So that basically just drop the C. And let R equal 1/2. Well, what you'd have is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot, dot, dot. Okay? Now, looking at that, I would tend to say that that's a pretty ugly 8, isn't it? Certainly the sequence is converging to 0, the sequence of those values in there. But the sum, this was sort of easy to see because if you start with 1, wherever that is, okay, 1, forget that one, let's just do this. This is 1/2 here, plus a 4th would be halfway between 1/2 and 1, plus another 1/8, and by the way, that 1/2 plus 1/4 is 3/4. And then when you add 1/8 to that, this would be 6/8 plus 1/8 would be 7/8. Add 1/16 to that, this would be 14 16ths plus 1/16 would be 15/16. And see, what you're doing is that age-old problem that if I were to walk half the distance from me to that desk, and then do another half the distance, and then another half the distance, and another half the, will I ever reach the desk? I get close enough to touch it, yes, but if I'm only getting half the distance to the desk, technically I'll never quite get there. Okay? And that's exactly what this sequence is doing. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64. You're going halfway of the remaining distance, but you never get it. But that's going to 1. So this part is going to 1, then you had a 1 to begin with, so the sum of all that would be 2. 1 plus 1 is 2. Okay? So that's annex. Say again? It's what?
Is that converge?
Yes, it does. That one does converge. Absolutely. Okay? Adding the terms up corresponds moving stepwise from 0 to 1. Each step takes you half the distance of what's remaining, but you never get there, but you're getting closer and closer to 1. Okay? So, now, when you were in school somewhere down the line, did y'all ever develop a way to come up with the fractional representation of a repeating decimal? Do you remember if you ever did that? No. I remember we did, and it was sort of a fun process. The reason I ask is very similar to this one. Let's say, I think I'm going to start with a clean page here, just because this is going to take a little bit of writing. I don't want it to be so cramped you can't see. Why will that not? There we go. Okay. If you have a sequence, S of n, a series, partial sum, S of n, that is equal to C plus CR plus CR squared plus CR cubed plus, how many do they do? Dot, 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 plus CR to the n. See, this is a partial sum. We're only going to the nth term. Partial sum. Okay, that done. Now, what if we would multiply this partial sum by that same ratio, R, the common ratio that we had in there? What would happen? R times S sub n would be CR plus CR squared plus CR cubed. You're multiplying each term by R, right? Plus CR to the fourth plus dot, 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 plus CR to the n plus 1. You just multiply by another R. All right. Now, what I'm going to do, and it seems like a strange thing to do, is subtract these two. And I would have been tempted to subtract the other way, but they're doing it this way, so I'm going to do it. Subtract this one from that one. So subtract this from the one above. Okay? So this would be S sub n minus R times S sub n is equal to C plus CR minus CR plus CR squared minus CR squared. You see, this minus this, this minus this, this minus this, this minus this, all the way up to plus CR cubed minus CR cubed plus CR to the fourth minus CR to the fourth plus dot, 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 up to, and the very last term would be plus CR to the n minus CR to the n plus 1. All right. Just like our telescoping series before, these two add to 0, those add to 0, those add to 0, those add to 0. This one and one that was before add to 0. And what do you have? You have, okay, I'm going to simplify the left-hand side too. Have a common factor of S to the n. S sub n times 1 minus R is equal to C minus C R to the n plus 1, right? And what I want to know is what S sub n was. I wanted to add those things together, but I didn't want to take the time to do it, okay? So now I'm going to have it done for me. I'm going to divide both sides by 1 minus R. Okay? Well, what we have here is S sub n is equal to, I'm going to factor out the C too, and that's going to give me 1 minus R to the n plus 1 over 1 minus R. And that you get at the very bottom of the page. Do I even have it in the same form? I think I do. Okay? And let's see if they have it on the next slide. There it is. This is what the summation of an infinite a geometric, sorry, I can't talk. Sorry, my head's, throat's clogging up. This is the summation of a geometric series where your common ratio is R and C is the constant. Okay, they don't let C be zero, otherwise it's a very uninteresting problem. Everything's zero. Okay. So the sum is zero, the series is zero, everything's zero. So we don't use C equals zero. So it's that sum of this sequence is this. C times 1 minus R to the n plus 1 divided by whole thing divided by 1 minus R. Okay. Now let's just do a few observations about this. Certainly your ratio can't be 1 either, can it? That would be pretty uninteresting. Your answer looks like it should be just C then, but no, yeah, it would be. That would be C plus C plus C. If the ratio was 1, you don't want that. As infinite as the other. That would be NC, and that's not converging to anything. All right. But you can't have R equal 1 anyway, because then your denominator would be 0. So you don't want that either. Okay. Okay. I think that's about all we want to do. That formula enables you to sum a geometric series. Get to know it, okay? You can write it down, bring it with you, or you can have open book tests to take home. Hang on to that concept, okay? Any geometric sequence, okay? A series, I'm sorry. What you say? Oh, I thought. Oh, okay. Now, let me also say this about it. We say R, you don't want R being 1. You don't want R being 0 makes no sense. Let's just give you the number C. And sure enough, if R was 0, this would be 1. And if R was 0, always 0, this would be 0. So that would be 1. So you just have C. Sure enough, that's what you would have. So you don't want C being 0, you don't want R being 0, you don't want R being 1. Okay. Now, let's see what other possibility we have. If the R were a number, say, greater than 1, okay, R to the n plus 1 would be infinitely, well, it would be a very large number depending on how large n was. A very, very large number. 1 minus a very large number would be a very large negative number. And this would be divided by another negative number, which would be pretty good size. But the numerator would be much, much more negative than the denominator. So that's not going to work well. Okay? No matter what size C was. So, I think what we're getting at is R had better be less than 1. But does just being less than 1, does that do enough for you? I think it does. Okay, but we'll get to that later. Let's go to Theorem 2 and see what it says. Okay? I think it's getting at the same thing I was getting at. And they may do it a little more maybe elegantly or systematically than what I was just sort of randomly doing. My eyes are so dry. The sum of the geometric series, okay? Of course, we don't want C being 0. If C was 0, the whole thing's 0. It's not very interesting. Now, here's what we do want, and it's what I was suggesting. You can have a ratio of 1 or anything greater than 1. So we want the absolute value of R. R could be negative. Absolute value of R be less than 1. Okay? That's the case. Okay? The summation of that, this is not the partial sum, but the total summation of that would be what you do here. If R is less than 1, the absolute value of R is less than 1, in that previous form that we had, let's go, I hate to lose it, but if you just look on the page, bottom of the previous page, that R, if that's less than 1, when you raise it to an extraordinarily high power, that's going to go to 0. So you're left with just C in the numerator and 1 minus R in the denominator. So sure enough, this is what your geometric series gives you. If R is anything less than 1, and that's the absolute value of R less than 1, anywhere between minus 1 and 1, but not counting minus 1 and 1, anything in between those two numbers, except, of course, don't have R equals 0. Okay. I mean, you could, but if R was 0, you just have C. It won't give you that from the formula, but that's what you would have. Because all these terms would be 0. Okay. So, absolute value of R less than 1, and we'll just say, but R not 0. C is not 0. Okay. Now, that is if you start your sequence from n equals 0. Go from there. Now, if you start your sequence n equal m, not 0, and they don't say this, but generally m is going to be greater than 0, some positive number. Just sort of makes everything work a little better. Then what is your geometric series? Okay? Well, you're not starting with c equals 0 here, with n equals 0. You're starting with some other value. Okay? And that would be m. C r to the m plus c r to m plus 1 plus c r to m plus 2, c r to m plus 3, so on and so on and so on. Okay? Well, what does that do for us now? Well, if you were to factor out an r to the m from each of these terms, you'd have a c here, cr here, cr squared here, cr cubed. You would just have that. So you would have r to the m times what you had up here. And sure enough, that's what you get. So if you have a geometric sequence series that's starting at some number greater than 0, starting at 0, there's your sum. You're starting at a number greater than that, it's that sum multiplied by r to the m, wherever that m is starting. Remember, r being a number, absolute value less than 1, so this is going to be a number much less than 1, so that reduces your sum. Now, if r is either equal to plus or minus 1, or greater than plus 1, less than minus 1, the absolute value of that is greater than or equal 1, the geometric series diverges with no hope of converging at all. So the r, that's the requirement. R, absolute value of r has to be less than 1. Okay? Now they do a little proof, but then they go skip several examples. So let's do them here. Let's evaluate some things here. Here's a summation of n equals 0 to infinity of 5 to the negative m n power. Okay. Do you want to give me a few terms in that sequence, or do you want to use the formula? Let's do a few terms just to see what they look like. N equals 0, what would you have? 1 plus, second, 1 over 5 plus 1 over 25 plus 1 over 125 plus 1 over 625. I don't know anymore, so I'm just going to say dot, dot, dot. Okay. Now, looking at it that way, I'd say, yeah, it looks like a pretty good chance of its converging, wouldn't you? Because the other way to express this is the summation n equals 0 to infinity of 1 over 5 to the n. Okay? Well, what is that? What that is a geometric series, isn't it? Let's go back. It's a lot like the one, it doesn't have an example number, but 1 over 2 to the n. This is 1 over 5 to the n. Okay? Well, I think in here it's fairly easy to see your c is equal to 1, right? There is no common factor in it, it's just 1. And your r is equal to 1 over 5, right? And certainly that r is less than 1. Absolute value of that is less than 1, okay? So basically now, and this is going from 0 to infinity, and from theorem 2, top of the page there, that would be that infinite series, especially written in that form, that you see it a little bit better, that would be c, which is 1, over 1 minus r. What's 1 minus r? 1 over your r is 1/5, so this would be 5/5 minus 1/5 is 4/5, and that would be 5 over 4. Is that what you were saying? Yeah, okay. I thought maybe you had jumped to that step. So that does converge, and it converges to 5/4. Okay? Which kind of makes sense, because it's got to be something greater than 1, because you got a 1 added to whatever it is. All those terms are positive, so it's got to be something greater than 1. And all those other things add to something. They sure don't add to 1. If that were a 2 there, rather than a 5, that would add to 1. But no, it's not a 2. It's something that's less than 2. It's 1/5, and every subsequent term is less. That's adding to 5/4. Okay? Okay? The formula, if you look at under theorem 2, the summation, you see it, yeah. C over 1 minus r. C was 1, r was 1/5. Okay? Okay. No, I couldn't look at that and see it. I used the formula. Okay, yeah. All right. Let's look at example 4. Do we need to erase this? We might. So let's go on and do it rather than running out of room. I know what happened. I hardly drank anything. I just crammed down my salad and my sandwich and didn't have a chance to drink anything. So now everything is all dried up. That's why I'm having trouble breathing. Or at least that seems reasonable. Maybe not. All right, here's the one. The summation from n equal 3 to infinity of 7 times a minus 3/4 to the nth power. Okay. Now, before I did anything else, I don't know why the book doesn't do this. It just seems to be kind of crazy that they don't. But if you think back at Theorem 1 at the bottom of a page, in my book 525, you can factor out the 7. That's just the C there. Factor it out. So I don't know why they didn't do this. I would do 7 times the summation n equal 3 to infinity of negative 3/4 to the nth power. Okay? To me, that's far easier to work with than carrying every 7 every term. Okay? Now, what's that sum that we're left with now? Okay? Our r in this case, in fact, the c in this case is 7, and your r in this case is negative 3/4, right? Okay? And that absolute value of that is certainly less than 1. Okay? So, but this is starting at n is equal to 3. So we have that extra term to put in there, and that's r to the mth, and our m is now 3. So, according to our formula in Theorem 2, that summation that we have there is going to be 7 times r to the third power, because that's the m we're starting with, and that's over 1 minus, sorry, sorry, 1 minus r. But the r is minus 3/4. So this will be 7 times a negative 3/4 cubed divided by 1 minus a minus 3/4 would be 1 plus 3/4. Okay? What's that? 7 times, well, a negative sign cubed is going to be negative. Okay, so I'm going to put the minus out front. 3 cubed is 27, 4 cubed is 64, and that's divided by 4/4 plus 3/4 is 7/4. Okay? Now, I'm going to take this 7 here and divide out that 7 there. Done with that. This 4 here in the denominator will go into that 4 in the denominator 16 times. So this comes out being negative 27 over 16. Let's see. Yeah, yes, that's what they got to. If you want a decimal number, you can plug that in too. But you see, this nice little formula here, there's actually 2 of them. One when you start at n equals 0, one when you start at n equals m, any m. It can make life so much easier to calculate. Way easier. Okay? All right. It looks like example 5 is going to be a little bit of a, may not be a huge challenge, but it may have some. Did y'all finish this one? Do I need to leave it a little longer? Got it? Okay. Certainly, after class is over, we're going to run to the office and or water fountain and get something to drink. Let's do example 5. And by the way, were you anticipating the sum to come up negative? Okay. Don't know if you thought about it. It just happened to be the first term in that sequence was 7 times a minus 3/4. It's going to be a negative number, right? Okay. The next one is going to be positive, but it's going to be times 9/16, which is a little bit less than 3/4. So you're going to be adding to a negative number, adding a number less than that. Then you're going to subtract a number that's going to be less than the other. So you start at negative, no way you're ever going to get positive, okay? Because that was your biggest number, and every subsequent thing you're either adding or subtracting something smaller than the previous one. So yeah, you'll never get positive in that one. Okay, let's look at example 5. Find a fraction that has a repeated decimal. Can't believe they're doing this. Find a fraction that has a repeated decimal expression 0.2121212121. Okay? Now, I'm not going to do it the way they did because this is the way we learned it. Okay? It's the same thing, by the way. Okay? We want to find the decimal number. What do you want to let it be? Give me a variable. Is D as good as any? Okay, let's say that D equal, we want the decimal number that's equal to 0.212121 ... repeating decimal 2121212121. Okay? Now, look at the size of the repeating segment. 2 places, right? So let's multiply this by 100. 100D, right, would be what? Yeah, multiply this by 100, move the decimal 2 places, right? 21.212121, ... right? Now let's subtract them. This is much easier than what they're going to do, but we'll come back and do what they do. Subtract those from each other, right? That gives you how many D's? 100D minus 1D is 99 D's, right? Don't start singing bottles of beer on the wall. No, okay. That's equal to, and when you subtract these two numbers, look at what happens. All those decimals disappear. And you're just left with 21. And now I can tell you what that decimal number is. I mean, it was a decimal number. I was looking for a fractional number. I should have done F. I'm sorry. What was my thinking? Let's do that F. Okay. The fraction that's equal to that. Okay. You can leave it D. It doesn't matter. Okay. Divide both sides by 99. Okay. 99s go out, and that fractional number is, by the way, I know that 3 will go into both of those, 3 over 33. Right? And, no. 7 over 33. I can't divide. 7 over 33. There's the fractional number that's equal to that decimal. Okay? 7 over 33. And if any of you happen to have a calculator, why don't you plug in and do 7 divided by 33 and see what you get.
0.21.
Say again?
0.21.
212121212121. Yeah, that's what we started with. See how that works? That's why I asked you to begin with. Did you ever done this? That's how you get any repeating decimal into a fractional form. Multiply by the power of 10 of the number of repeating decimals. If that was a 0.4152, 0.4152, 4152, 4152, 4152, then however many decimals that is, the zeros after the 1. Or, even if it was 74121412141214121, multiplied by the 110 for the 7, and then the other 3 for the, did I say 421? Whatever I said, okay. And so that you do by 4, and then when you subtract the, try it, play with it, you'll see that it works out. Okay. Now, what they do is very similar to what we did, is that we can write that decimal as a series, and I never would have thought of doing this, or never would have wanted to do this. They say this is 21 over 100 plus 21 over 100 squared plus 21 over 100 cubed. Okay, sure, it is that, but I'm not sure I would have looked at that and said that's what it is, but that, you know that the first 2 digits there represent 21 over 100, right? You know that, okay? But the next one was 21 over 100 squared. which would give you 4 decimals, and sure enough, that'd be 21 over 10,000, 2, 3, 4, yeah, plus 21 over 100 cubed plus 21 over 100 to the 4th plus ... Let's just leave it alone like that. Well, that's a geometric series. Your C here is 21. Your R here is every term is 1/100th times the previous term, right? So it's 1 over 100. That's certainly less than 1, okay? So what, and you're starting, let's see, where are you starting from here? You're not starting from n equals 0, you're starting from n equal 1. Aren't you? I think so, okay? So since you're starting from n equal 1, now why in the world do they say A is equal to? Oh no, I see what they do. They say the C is 21 over 100, and then you are starting from 0, okay, because the first one's just 1, okay. And then your R is 1 over 100. You could do it either way, but that works just as well. And then, since you are using that one, then it would be C over 1 minus R. And that would be 21 over 100 over 900, 99 over 100. Because 1 minus 1 over 100 is 99 over 100. The hundreds go out, you got 21/99ths, which again reduces to 7/33. Okay. Get the same answer. I think the way we did it was actually much easier, but they're trying to get you used to thinking in terms of geometric sequences. Okay, example 6. How are we doing? Yeah, we're fine. Okay. Evaluate this sum, infinite sum, series, let's call it a series, is equal to the summation n equals 0, that gives me a little sigh of relief, to infinity of 2 plus 3 to the nth over 5 to the nth. Okay. Houston, do we have a problem? A little one. Okay? What you have to do is write this as 2 series. Not 1, but 2. The first of these series, and this comes from the linearity of series, infinite series, this is okay to do. That would be the summation from n equals 0 to infinity of 2 over 5 to the n, right? Plus the summation from n equals 0 to infinity of 3 to the n over 5 to the n. That works, doesn't it? Okay? You just split that 2 over 5, 2 plus 3 to n over 5 to n is 2 over 5 to n plus 3. Yeah. It's adding fractions in reverse, okay? You just split the numerator. Okay. Now, on that first one, your C is what? 2. What is your R? 1 over 5, right? And you're starting from 0, so what do we have? C over 1 minus R, which would be 2 divided by 4/5. And now don't know if this is okay. Well, let's do it this way. S equal to 2 times 5 over 4, right? Dividing by a fraction, invert and multiply. So that would be 5 halves. 2.5. That's what that first one adds up to. Okay? Now, okay, I'm sorry. Okay. Now, how about the next one? The next one, your C is 1. And your R is 3/5, right? Okay. Now, your summation there would be 1 over 2/5, which would be 5 halves, wouldn't it? And then add those two together. 5 halves plus 5 halves is equal to 5. Amazing, but true. That just adds to the number 5. 10 halves, which is 5. I glanced down, which I thought they were just doing the first one, and saw 5. I said, no, it's 5 halves. Why you got 5? And then I realized that fits. Okay. Now, there is a little conceptual insight here. Let's take a look at that quickly. And sometimes I wonder why they do things like this. Okay. Oh, I see. Okay. Why couldn't they have chosen? Well, they do choose one. Okay. They start with a sequence here. I mean a series. I keep saying sequence. So use the last section. They start with a series here of 1/2 plus 1/4 plus 1/8 plus ... Okay? Now, and they do a procedure on it, and then they say, that gives you the right answer, but how do you know it's right? Well, just looking at it would tell you that would be okay. Does this sequence converge? The series converge. Sequence does, obviously, but does series converge? Well, what's your common factor? 1/2. Okay? So, yeah, it's going to converge. So any technique you use that's going to give you a right answer will do it. Okay? So what they do, and let this be the series, and then they say, multiply this series by 2, which is okay to do. 2 times 1/2 is 1. 2 times 1/2 is 1. 2 times 1/4 is 1/2. 2 times 1/8 is 1/4. 2 times 1/16 is 1/8, and keep on going infinitely. And then subtract those from each other, and you have, subtract this one from that one. Okay, so this is the minus. Okay, and that gives you S is equal to 1, because all these subtract away. And sure enough, S is equal to 1 is an answer. They do have the 1. That's the one we did to begin with. 1/2 plus 1/4 plus 1/8. You're getting closer and closer to 1. So that's okay to do. Okay? But then they give you one that's not. Okay? What if this was your series? S is equal to 1 plus 2 plus 4 plus 8 plus 16. Do you think that converges? No, no way. It's going to infinity really fast, okay? So can you use the same technique you just did? Don't even try it. It doesn't converge to begin with, but they say, so double each term, double the series, 2s is equal to 2 when you double 1, plus 4, plus 8, plus 16, plus ... I didn't put those in. And when you subtract those from each other, you get negative s is equal to 1, so s is equal to minus 1. Do you think there's any way that series is going to sum to negative 1? No. It couldn't. It didn't converge to begin with, so you can't use these techniques to, so that to me was, maybe I shouldn't have even given it as much expression as I did. All right, how about the infinite series summation of 1, k equal 1 to infinity? No, it can't possibly converge. Because 1 plus 1 plus 1 plus 1 plus 1, it gets bigger, infinitely bigger. Okay? Oh, we're out of time. We'll start there next time. We'll start with that infinite series. I was going to try to get to theorem 3, but I didn't make it. We came close to finishing 10.2, though. Homework exercises here. I think you can do it. Do number 1. It has 4 parts. Do either 3 or 5 or both. I'll let you choose. Do 7. Do 9. Now it says you need a computer algebra system. If you find it too much to do and you don't have that, don't sweat it. Okay. Then I'd say do any of the odds 11 through 15. Then do any of the odds no. Stop there. 11 through 15. I think you can do those. The next ones start with theorem 3, and we haven't done theorem 3 yet. Okay. Well, yeah. They have different names for it. All right, good deal. One thing I would like to just wonder about a little bit. In 3 of my classes, I believe, I've had a paper turned in. In this class? No, okay. Don't be putting this off till the end of the term. You're going to have plenty to do at the end of the term. Get working on it. Take advantage of some of this each time. And by the way, we're only going to do these 2 sections in Chapter 10. Then we'll just do 2 sections in Chapter 11. Then I'll give you a quick test on the first, on 10 and 11. Then we'll go to 12, which we're going to do more of. Can't remember how much we do. Let's see. Yeah, we're going to do most of that. So we'll then have a test on Chapter 12. Okay, so we'll have a short test on 10.1, 10.2, 11.1, and 11.2. All right. Have a good week. Well, let's see. Yeah, I won't see y'all anymore. Have a good weekend now.